We believe we have discovered thousands of black holes across the universe. Dark, massive objects that leave gravitational signatures seemingly impossible to mistake. Yet, at the very center of that belief, a quiet paradox remains. We have never directly observed an event horizon. No telescope has ever captured that boundary through light or an unambiguous signal. The event horizon is inferred, never truly seen. So what if an object exists that looks like a black hole in every measurement we can perform? It bends space-time exactly as general relativity predicts. It governs the motion of stars and gas according to every familiar model. It produces signals we have learned to label as black hole signatures. Yet deep inside, it has no event horizon at all. This is not a science fiction scenario. A gravastar is not born from imagination, but from the equations of general relativity itself. It is built upon the same mathematical foundation that has described gravity for over a century. And its possible existence poses an uncomfortable question for modern science. Are our current observations truly sufficient to tell the difference? In the end, what does science actually rely on to say an object is a black hole and not a gravastar? When we talk about black holes, the most common intuition is darkness, a region that emits no light, reflects nothing, and seems to swallow everything nearby. But in physics, that is not how a black hole is defined. A black hole is not defined by how dark it appears. It is defined by a far deeper mathematical and physical concept. That concept is called the event horizon. An event horizon is not a physical surface. It is a causal boundary in space-time. Once this boundary is crossed, no signal can ever return. No light. No particle. No information. That property is what truly defines a black hole. The problem is that an event horizon emits no light. It does not reflect or interact directly with any measuring instrument. No telescope can photograph an event horizon in the ordinary sense. We can only infer its existence through indirect consequences. And this leads to an unavoidable question. If the event horizon cannot be measured directly, what exactly are we certain about? When we label an object in the universe as a black hole, when testing black holes through direct observation, we often point to the famous image of the shadow. These images come from the Event Horizon Telescope, a global network of observatories operating as an Earth-sized instrument. What the EHT observes is a bright ring surrounding a dark central region. That bright ring is often interpreted as strong visual evidence for the existence of an event horizon. Physically, however, this image requires a more careful interpretation. What we actually see is not the black hole itself. It is light emitted by the accretion disk. Hot gas and plasma orbiting at near light speed. This light is strongly bent by extreme gravity before reaching our telescopes. The dark region at the center is not an imaged surface. It is a region from which photons cannot escape toward the observer. Crucially, this shadow region does not coincide exactly with the event horizon. It is largely determined by photon orbits and the space-time geometry near the compact object. Theoretical models reveal something remarkable. Gravastars and many horizonless objects can still produce bright rings and dark regions almost indistinguishable from black holes. As long as the gravitational field is sufficiently strong and compact. In other words, EHT images test gravitational geometry extremely well, but they do not directly test the existence of an event horizon. This leads to an uncomfortable conclusion. If images alone are insufficient, we cannot be certain we are distinguishing a black hole from a gravastar. So if images are not enough to tell them apart, what other measurements do we have left? If images cannot reach the event horizon, science must turn to a more stringent channel. That channel is gravitational waves. When two compact objects spiral toward each other and merge, they disturb the very fabric of space-time itself. These disturbances propagate outward as gravitational waves. Detectors like LIGO and Virgo do not observe light. They directly measure tiny stretches and squeezes of space-time. For black holes, the gravitational wave signal has a very specific structure. After the violent merger, the system enters a phase known as ring-down. During this phase, the newly formed black hole oscillates and settles. These oscillations are described by highly specific quasi-normal modes. Their frequencies and damping rates depend only on mass and spin. No knowledge of the prior history is required. This is a powerful prediction of general relativity, and so far, observed signals match black hole models remarkably well. But what if the merging object has no event horizon? For gravastars, theory predicts the post-merger behavior may differ. Instead of fully absorbing oscillations, the internal structure may respond. This could alter the oscillation modes or generate additional signals. In principle, gravitational waves could carry information that distinguishes the two scenarios. The problem lies in the magnitude of those differences. Many models show they are extremely subtle and easily buried beneath noise and measurement uncertainty. This leads to the key question: is the difference in gravitational waves large enough for current detectors to observe? When discussing gravitational waves and event horizons, one idea has sparked years of controversy. That idea is known as gravitational wave echoes. Some studies claim that after the merger of two compact objects, the gravitational wave signal does not end cleanly with the ring-down phase. Instead, faint, repeated pulses may appear later in time. These pulses are referred to as echoes. In theory, they would only appear if no event horizon exists. If the object has a surface or an internal reflective structure, gravitational waves could bounce back multiple times before escaping. In this scenario, echoes are interpreted as signatures of gravastars or other horizonless ultra-compact objects. However, the challenge lies in detecting such signals. If they exist, echoes are predicted to be extremely weak. They sit dangerously close to the noise floor of detectors. Many other research groups have reanalyzed the same data, and they argue that the reported echoes are simply consequences of statistical noise and model selection. Small changes in signal filtering can make echoes appear or disappear entirely. This is not the hallmark of a robust discovery. At present, no echo is regarded as confirmed by the gravitational wave community. No result has crossed the threshold of broad scientific consensus. This raises a deeper question. If the expected signal is intrinsically too weak, could gravastars be existing beyond the reach of our current measurement capabilities? A natural scientific instinct is to believe that greater precision will resolve every ambiguity. If we can infer the radius of an object with extreme accuracy, then the boundary between black holes and other objects should become clear. In practice, there are astrophysical systems whose inferred radius lies almost exactly at the Schwarzschild radius. The precision of such measurements can reach dozens of significant digits. This is often taken as near definitive evidence for black holes. But here, intuition turns out to be misleading. Gravastar models reveal a different possibility. An object without an event horizon can still be compressed to smaller than 9/8 of the Schwarzschild radius. And, in principle, it can approach that boundary arbitrarily closely. There is no sharp limit forcing it to become a black hole. As the radius moves ever closer, the external observational signatures become increasingly indistinguishable from those of a black hole. Image, stellar motions, radiation spectra, all converge toward the same outcome. The paradox is that the more precisely we measure, the conceptual boundary becomes more blurred. Precision does not eliminate uncertainty. It merely pushes it to a deeper threshold. At that threshold, the difference between having and not having an event horizon may be smaller than any finite measurement can resolve. And this leads to an unavoidable question. Are we approaching a fundamental limit of observation, where the true nature of the object can no longer be distinguished experimentally? After all, measurements, image, and signals, we arrive at an unusual point. There is no evidence forcing us to deny the existence of black holes. Yet there is also no measurement strong enough to conclusively rule out gravastars. Both possibilities are theoretically valid, and with our current observational capabilities, they can produce external signatures that are nearly indistinguishable. This is not merely a technical issue. It touches a foundational question of science itself. In the scientific tradition, a concept carries meaning only if it can be tested and potentially falsified. Falsifiability is not a weakness. It is what gives science its strength. But what happens when two different descriptions of reality cannot be distinguished by any available measurement? In that case, where does the difference actually reside? Is it still a physical difference? Or merely a difference in how we interpret equations? It may be that black holes are how the universe naturally ends gravitational collapse. It may also be that gravastars represent a more subtle configuration, avoiding an event horizon while mimicking every external consequence. For observational science, if no measurement can distinguish between the two scenarios, then assigning labels becomes unclear. We may be naming the same phenomenon using different conceptual frameworks, and this leads to the final question. If an object cannot be distinguished by every measurement science can perform, does its difference still carry genuine physical meaning? As the full chain of reasoning comes to a close, one thing becomes clear. Gravastars have never been ruled out by any current observation. At the same time, there is no evidence that denies the existence of black holes. Both possibilities coexist within the theoretical landscape of modern physics. The issue is not a lack of data. We have images, gravitational waves, weak stellar orbits, radiation spectra. The problem lies in the limits of how we observe the universe. There may exist structures in the universe that are entirely valid from a physical standpoint, obeying every equation we trust. Yet they do not allow a definitive experimental verdict, not because they are mysterious, but because they sit precisely at the boundary of scientific knowledge. At that boundary, observation is no longer sufficient to distinguish internal nature. Science can still describe external consequences with precision, but it cannot reach the final answer. And perhaps this is the most thought-provoking point of all. The most important question may not be whether it is a black hole or a gravastar. Rather, whether the universe contains entities that science can only name, but never be completely certain it understands. Perhaps the greatest limit of science is not what we have yet to observe, but what, in principle, cannot be distinguished.